Sige, Mr. Alonso. You can start.
Few years ago, many incidents happened in a disastrous way, includes the earthquake and tsunamis. It has been discussed na rin sa mga nagdaanang reports kung ano nga ba ang naging causes ng mga ito. As you see on the presentation, effects of soil on ground motion liquefaction will be talked through and subtopics on it will be tackled later on. Kung titingin tayo sa paligid natin, structures are built in different shapes and sizes. Katulad ng mga nakikita niyong letrato, mostly ay buildings, di ba? Gumuha sila or nasira dahil sa ground failures na nangyari sa pinagtatayuan ng lupa. Siyempre, kinukonsider rin ng mga engineers sa mga wavelengths na maaaring makaapekto sa pinagtatayuan nito because it threatens the life safety of people na titira dito. All structures have at least one feature in common. They all have foundation. At ang foundation ay ang kumokonekta sa lupa upang suportahan ang structure at maiwasan ang pagguhunga nito. Under static conditions, generally only the vertical loads of structures need be transferred to the supporting soil or rock. In a seismic environment, the loads imposed on a foundation from a structure under seismic excitation, maaari nitong magpasa ng mga vertical loadings. And there will be horizontal forces na kung saan ay magiging antas ng pundasyon. An earthquake might cause the phenomenon of liquefaction to occur in loose sandy soils, which would cause a virtually complete loss of all bearing capacity of the soil. So, yung nagsusupport ng weights, mawawala ng capacity na magdala ng mga loads na magre-resulta naman sa structure para siya ay mag-unbalance, tumagilid. Once na yung soil, na mag-behave as liquid or lumambot, ganon. Ito nga sabi, needless to say, a structure founded on such shores would suffer great distress and upset. Let's take a look at this picture. Itong unang picture muna, bearing capacity failure. Ang kakita nyo, lumubog yung yung konting part ng down corner ng structure. Tapos, ito namang sunod, yung pangalawa, ito na yung itsura nung nag-tilt yung structure. Ayan. Some of these phenomena can be effectively designed for by structural detailing, but some of these phenomena are beyond the magic and wizardry of the structural engineering profession, and geotechnical wizardry may also be needed. In a seismic environment, there may exist a potential for ground failures. Several different ground failure mechanisms includes soil liquefaction, settlement, subsidence, differential compaction, landsliding and lurching, flooding, tsunamis, and sea. The Turnagain Heights landslide occurred as a result of the 1964 Great Alaska Earthquake and had length of about 1.5 mile and width from 1/4 to 1/2 mile. Pero, paano nga ba na-damage itong Turnagain Heights na to during the 1964 earthquake? According to my research, the buried Bootlegger Cove clay layer field, resulting in numerous landslides. The epicenter of the Richter magnitude 8.5 earthquake was about 130 kilometers from Anchorage, pero ang duration ng strong ground motion ay tumagal ng lagpas 3 minuto. However, Sid and Wilson believed that the long duration of the ground motion caused the poor water pressures to continually increase, causing liquefaction of silt and fine sand lenses, which led to
action. The scales of socio-economic damages caused by an earthquake depends to a great extent on the characteristics of the strong ground motion. It has been well known that Earthquake ground motions results primarily from the three factors, namely source characteristics, propagation path of waves, and local site conditions. When an earthquake strikes, the intensity of earthquake shaking determines the severity of damage. An earthquake radiates through the earth from the epicenter. When the seismic waves travel through soil, it changes how the vibrations are felt on the ground. The earthquake vibrations then transfer up through buildings, which again changes how we feel the earthquake if we're inside the building. One factor with a significant effect on shaking's density is the type of soil. Soils can be classified as flexible, rigid, or somewhere in the middle. Another factor that significantly affects shaking intensity is the structural configuration of the building being shaken. Each building absorbs and transmits seismic waves differently, depending on its natural period of vibration. The first factor affecting a building's natural period is its material type, either steel or concrete or wood. The second factor is the spacing and arrangement of columns, walls, bracing, including the amount of reinforcement. Third, but perhaps most significant, the height of the building affects its natural period. Generally, taller buildings are more flexible and tend to sway, while shorter buildings are more rigid and tend to quiver or pulse. In the language of physics and structural engineering, the taller, sway buildings attract and transmit less earthquake acceleration, whereas the shorter pulse buildings experience higher earthquake accelerations.
Seismic soil structure interaction. It refers to the influence that the ground has on the behavior of a structure placed on it when subjected to different types of loads. The soil structure interaction problem has become an important feature of structural engineering with the advent of massive constructions on soft soils such as nuclear power plants, concrete, and earth dams. Buildings, bridges, tunnels, and underground structures may also require particular attention to the given problem of SSI. If a lightweight, flexible structure is built on a very steep rock foundation, a valid assumption is that the input motion at the base of the structure is the same as the free field earthquake motion. As a result of the increased duration of the vibration period, which should reduce the magnitude of seismic accelerations acting on the structure, the concept of soil-structure interactions has become widely accepted in structural engineering design.
If the structure is supported on soft soil deposit, the inability of the foundation to conform to the deformation of the free field motion would cause the motion of the base of the structure to deviate from the free field motion. Also, the dynamic response of the structure itself would induce deformation of the supporting soil. So, yung mga effects daw po nito na ay mas significant para sa mga heavy structures na supported on relatively soft soils. Then, para naman po sa mga soft and light structures, ang effects daw po nito ay parang medyo maliit lang. But it is also significant para sa mga closely spaced structure na merong mga pounding when the relative displacement is large. And to better understand po, it is necessary to have information of the earthquake wave propagation sa pamamagitan ng soil medium. Una po ay kapag ang mga seismic wave ay kumakalat sa lupa bilang input ground motion, yung dynamic characteristics po niya ay nakadepende sa pagbabago ng mga bedrock motion. Pangalawa, yung mga knowledge natin regarding sa mga vibration characteristics ng mga soil medium ay makakatulong sa atin para ma-determine ang soil impedance functions kapag ang wave propagation analysis ay pinerform by using numerical techniques. Sa mga older design techniques naman po, ang mga SSI effects were often ignored. and the structure was planned with a fixed or very rigid foundation to compensate for them. Para naman po sa mga light and small buildings on reasonably stiff soils such as dwellings or retaining walls, this would be most likely be acceptable since wala naman pong loss ng coherence across various places of the foundation. And nagde-decrease po yung amount ng dynamic amplification na nag-o-occur. The SSI effects on weaker soil grow more significant with heavier and bigger structures, such as nuclear power plants, high-rise buildings, and huge bridges, where ground motion incoherency and local differences in the soil profile may have a significant impact on the behavior of the structure. Free field motion and fixed space structures. Ground motions that are not influenced by the presence of structure are referred as free field motions. If the building is founded on soft soils, the earthquake motion at the base of the building is not likely to be identical to the free field ground motion. The presence of this structure will modify the free field motions because the soil and structure will interact to create a dynamic system quite different from just a free field condition. Katulad lang po na sinabi ko kanina na para sa mga soft and light structures na matatagpuan natin sa stiff soil, yung effects po niya dito ay generally small. Seismic response of a structure is dependent upon the nature of supporting soil. Severe structural damages to houses and man-made structures during many past earthquakes are observed to be concentrated in an area or the ground considered of local alluvial deposits. And the comprehensive assessment of free field motion ay dapat nating i-consider yung source characteristics as well as geotechnical and geological site conditions. The free field surface motions ang resulta ng reflection, refraction, and surface wave propagation. Ang major factors modifying the free field surface motions ay ang mga lalim ng lupa, column, the dynamic properties ng layers ng mga lupa, the type of rock strata, at ang mga properties ng ground motion. Structures founded on rock are considered as fixed base structures. When a structure founded on solid rock is subjected to an earthquake, the extremely high stiffness of the rock constrains the rock motion to be very close to the free field motion. Rocking of the structure would not develop in a fixed base condition. The reaction of the building sa mga earthquake ay nakadepende sa two major parameters. Una ay ang techniques na ginamit para sa kanyang construction, and pangalawa yung kind ng ground na kanyang pinagtatayuan. Buildings na nasa mga solid bedrock tend to shake less than buildings na nasa mga sediments or reclaimed lands because yung bedrock mismo nagshe-shake siya ng less than sediments or reclaimed lands. The bedrock naman vibrates a lot less than sediments because of kanyang structure. Kasi ang bedrock is much more compact than the sediments. Soft materials such as unconsolidated sedimentary deposits like bay muds and even sedimentary rocks amplify the shaking. Consequently, locations situated over sedimentary basins or on unconsolidated sedimentary deposits can be especially susceptible to strong shaking.
Effects. 1. Basin soil effect on the ground motion characteristics. Impedance contrast. Seismic waves travel faster in hard rocks in compared to softer rocks and sediments. As the waves passes from harder to softer rocks, they become slow and must get bigger in amplitude to carry the same amount of energy. According to Fiscal 2006, the shaking tends to be stronger at sites with softer surface layers, where seismic waves move slowly. Impedance contrast defined as the product of velocity and density of the material. Resonance. Various spectral peaks characterize resonance patterns. The frequencies of these peaks are related to the surface layers, thickness, and velocities. Further, the amplitude of spectral peaks are related mainly to the impedance contrast between the superficial layer and underlying bedrock, to sediment dumping, to a somewhat lesser extent to the characteristic of the incident wave field. When the signal frequency matches with the fundamental frequency or higher harmonic of the soil layer, we say that they are in resonance with one another. This results into tremendous increase in ground motion amplification. Dumping in soil. Absorption of energy occurs due to imperfect elastic properties of medium in which the particles of a medium do not react perfectly elastically with their neighbor, and a part of energy in the waves is lost instead of being transferred through medium after each cycle. Dumping of soil mainly affects the amplitude of the surface waves. This type of attenuation of the seismic wave is described by a parameter called a quality factor. It is defined as the fractional loss of energy per cycle, where delta E is the energy loss in one cycle and E is the total elastic energy stored in the wave. If we consider the damping of a seismic wave as a function of the distance and amplitude of seismic wave, we have where alpha is called the absorption coefficient and is inversely proportional to quality factor Q. Basin edge effect. When the seismic waves incident near the basin edge, it enters the basin from its edge and travel in the direction in which the basin is thickening. Interference of trap waves generates surface waves, which propagate across the basin. It shows that when the wave can become trapped within the basin, a post-critical incident angles develop. Waves that become trapped in deep sedimentary basins can produce stronger amplitudes and intermediate and low frequencies than those recorded on comparable surface material outside basin, and their duration can be twice as long. This basin edge effect can amplify long-period components of ground motion and significantly increases the duration of strong shaking. Basin-induced surface waves cause intense damage which is confined in a narrow strip parallel to the edge. Schematic diagram showing that seismic waves entering a sedimentary layer from below will resonate within the layer but escape if layer is flat, but become trapped in the layer if its varying thickness and waves enters the layer through its edge. Basement topography. Irregular basement topography, when the subjects to the body waves incidence below, results in focusing and defocusing effects. These effects are strongly depends on the azimuth and angle of incident waves. It shows seismic waves traveling in the upward direction from depth may be redirected by subtle irregularities at geological interfaces. As waves pass from the different unit across the curved interface, their velocity and direction changes, and once again changes at the unit nearest to the surface. Sometimes they meet at certain points on the surface. At this point, the amplification and the amplification constitute to focusing and defocusing phenomenon. Trapping of waves. Due to the large impedance contrast between the soft sediment and underlying bedrock, seismic waves trap over soft sediments. This results in increase in the duration of ground motion. When layers are horizontal, this trapping affects only body waves. While in case of lateral heterogeneities, this trapping also affect the surface waves. Interference of these waves also leads to resonance pattern. As discussed earlier, the base and edge effect cause the total reflection of the wave and the base of the layer, making them potentially very damaging. Number 2. Effect of surface topography. Effect of ridge. The ridge causes strong generation of surface wave near the top of the ridge and their propagation towards the base of the ridge. Amplification of the ground motion depends on the slope and elevation of the ridge. Effect valley. It has been predicted numerically that in the valley, due to the focusing effect, the amplification of the amplitude of motion take place. The intensity in the valley may be 1 to 2 scales lesser as compared to with the surrounding. It is free from the soil deposits. Slope effect. Hills with variable slope reveals complicated damage pattern. The houses situated on the near the bank of steeply sloping hills suffers more damages as compared to the houses which were at some distance away from the steep portion or are on the gentle sloping part of the same hill. Strong lateral discontinuity effect. Lateral discontinuities are nothing but the area where a softer material lies beside a more rigid one. For instance, ancient faults, anomalous contacts, debris zones, etc. The best example of damage caused by strong lateral discontinuity, softer rock sandwiched between hard rocks, was observed in the Batuari Sonary Village during Gamola earthquake of 1999. The village, situated on a sloping hill at the left bank of river Mandakini, received greater damage. The hill mass is composed of rounded pebbles and young soil, and it's surrounded by hard, older quartz-sized rocks. Amplitude amplification generation of local surface waves in the softer, medium, and larger differential motion caused by shorter wavelength of the surface waves may be reason behind the greater structural damage. Degree of influence of SSI. The degree of influence of SSI on response of structure depends on the following factors: stiffness of soil, dynamic characteristic of structure itself, and for example, natural period of damping factor, stiffness and mass of structure.
Interaction between ground and structure during earthquake. When the seismic wave E0 generated by an earthquake fault reaches the bottom of the foundation, they are divided into two types: transmission waves, which are entering in the building shown as E1, and reflection waves, which are reflected back into the ground shown as F0. The waves which are transmitted to the ground, known as radiation waves, shown as R1. The damping caused by radiation waves is popularly known as radiation damping of the soil. So alam naman natin na yung earthquake ay nagproproduce ng seismic wave. So yung wave na yon, nagtatravel siya paakyat, and kapag na-reach niya na yung pinaka-bottom or yung pinaka-foundation ng structure, nahati siya sa dalawa. So, yung dalawang yun ay yung transmission wave tsaka yung radiation wave. Yung transmission wave, yun yung wave na nag-enter sa building, which is itong E1. And then, yung isang wave naman is yung mga wave na bumabalik pababa sa ground, which is itong F0 or tinatawag na radiation wave. So, yung transmission wave or yung wave na nag-enter nga dun sa building, nagtatravel siya paakyat doon sa building. So, siya din yung nagkakos ng vibration ng building. So, pag na-reach niya na yung pinaka-top ng structure or ng building, magta-travel ulit siya pababa, which is itong F1. And then, kapag na-reach niya na ulit yung pinaka-bottom part, so doon nangyayari yung soil structure interaction. So, sa bottom part, doon ulit mahahati sa dalawa yung waves. So, merong waves na bababa na pabalik ng ground, which is itong R1, or yung tinatawag ng radiation waves. Meron din namang mga waves na aakyat ulit pataas dun sa structure, which is itong F2, or yung transmission waves nga. So, hanggat merong transmission waves na natatrap dun sa loob ng building, hindi titigil yung vibration niya. So, titigil lang yan kapag lahat ng wave ay naging radiation wave na. So, similar siya sa lightly damped structure. So, yung damping naman, dahil sa radiation, ay tinatawag nga na radiation damping of soil. So, dahil sa radiation damping na yon, nag-i-increase yung total damping ng soil structure system compared dun sa mismong structure. And dahil din sa influence ng soil structure interaction, yung mga natural frequency ng soil structure system is mas mababa kaysa dun sa natural frequency ng soil. And dahil din sa mga interactions na yon, nag-i-increase yung overall displacement ng mismong structure kasi nga pwede mag-translate or mag-rotate yung foundation ng structure. Fault rupture. Fault rupture and the associated ground deformation can have extremely severe consequences to structures and systems that cross the fault plane. The fault displacements can range from a few millimeters to several meters. So, if ever nga magkaroon ng fault rupture sa mismong kinatatayuan ng structure, sobrang laki nung magiging epekto nun sa structure and malaki din yung possible na maging damage nun. So, ito naman yung ilang examples ng mga structures na na-damage dahil sa fault rupture. So, etong una ay surface fault rupture up to 6 meters horizontal movement in the 1992 Landers earthquake. So, nangyari to noong June 28, 1992 sa Landers, California. And nagkaroon ng 7.3 magnitude earthquake. So, yung maximum horizontal displacement neto ay up to 6 meters across the fault. So, if nagkataon na marong structures dyan na nakatayo, sobrang magiging malaki yung damage ng structure and possible na mag-collapse talaga yung mga structure na nakatayo. The next naman is itong surface fault rupture beneath reinforced concrete dam in the 1999 Chichi, Taiwan earthquake. So, yung fault rupture naman is nangyari dun sa mismong kinatatayuan ng dam. So, malaki yung naging damage dun sa dam. And ito ay nangyari sa Taiwan noong 1999. So, nagkaroon ng 9 meters vertical fault offset sa Chalungpo Fault. So, iyan yung naging resulta nun. Nasira yung dam. And then last is itong building damaged by faulting during the 1999 Chichi, Taiwan earthquake. So, sabay lang tong earthquake na nangyari. And then, meron ding fault rupture na nangyari sa kinatatayuan ng building na to. So, medyo nasira siya. Although, hindi siya totally nag-collapse, mapapansin pa din yung naging damage dun sa building. So, ilan lang yan sa examples kapag dun mismo sa kinatatayuan ng structure nangyari yung fault rupture.
Liquefaction. Liquefaction is a physical process that takes place during some earthquakes. Liquefaction may lead to ground failure. As a consequence of liquefaction, soft, young, water-saturated, well-sorted, fine-grained sands and silts behave as viscous fluids. Liquefaction takes place when seismic shear waves pass through a saturated granular soil layer. So, liquefaction. It takes place when loosely packed water-like sediments at or near the ground surface lose their strength in response to strong ground shaking. Simply, a solid to liquid phase where the soil tends to liquefy whenever some earthquake occurs. Nalilesen ang compactness ng lupa dahil sa earthquake. Yung strength at stiffness ng soil ay naaapektuhan sa malakas na pagyanig ng lupa, kung saan naghihiwa-hiwalay ang soil particles na nagiging sanhi ng pagiging sun-like fine-grained sands ng lupa. May mga example dito ng effects ng liquefaction sa isang lugar. Una, yung liquefaction-induced road failure exposed cross-section of underlying soils and failure of bridges due to liquefaction. Here is a short video that will explain more about liquefaction.
What is liquefaction? Liquefaction is a phenomenon that occurs when loose, saturated, cohesionless soils lose their shear strength and stiffness and behave as quicksand during and after a seismic event. During earthquake shaking, loose silts and sands tend to densify into a tighter configuration. In cases where these soils exist above the water table, this densification results in small volume changes but no loss of bearing capacity or shear strength. However, when loose silts and sands are located below the water table and are saturated, liquefaction can be a concern. Because water is essentially incompressible, any densification of these soils due to a seismic event results in an increase in pressure in the pore water between the soil's grains. When this pore water pressure reaches approximately 60% of the soil's strength, loose silts and sands can lose grain-to-grain contact and liquefy. This phenomenon can have catastrophic effects on both above and below ground structures. Liquefaction can result in bearing capacity failures, lateral spreading, and intolerable settlements for bridges, roadways, and embankments. It can also cause intolerable differential and total settlements, and in some cases, a total loss of bearing capacity for buildings and above-ground structures. Structures constructed in the ground below the water table rely on the weight and strength of the overburdened soils. In seismic zones, liquefaction of near-surface sands causes these air-filled tunnels and utilities to float to the ground surface.
How does soil liquefaction work? Soil liquefaction occurs due to sudden and rapid load on the soil particle. The sudden water pressure leads to soil losing its cohesive strength. Once the soil loses its cohesion, it gets softened, weak, and loses its solid properties that are converted to liquid properties. The soil is a mixture of soil particles that stay connected together. Here, the effective stress controls the strain or stress behavior of soil. Yung effective stress ay yung force acted for the purpose na magdikit-dikit ang particles ng soil. These contact forces together hold all the individual particles of soil in their places. Due to earthquake, soil loses its strength and unti-unting naghihiwa-hiwalay, nawawala yung property ng soil, yung stiffness ng soil, and then nako-convert ito into liquid properties. From soil particles having contact in between to soil particles floating due to the increase of pore water pressure, the water infiltrated which reached the water table, then due to high pressure sa pagyanig ng lupa ay unti-unting tumataas papunta sa ground surface. Doon na nabubuo yung mga sand particles from the liquefied sand. Liquefaction during seismic events. Seismic events affect ground conditions. Liquefaction of soil causes structural instability in buildings. This occurs due to various instances of structural failure. The liquefied ground cannot sustain the stresses of its load from the foundations. Foundations will sink into the sand deposits and cause the building to lean and eventually collapse. Soil liquefaction occurs only in areas which have saturated soils. Most of these areas are located near a water body such as lakes, ponds, rivers, and many more. The soil can sustain the ground forces in general condition, but an earthquake or strong motion vibrations in the grounds can cause water logging, which increases the liquid consistency in the soil. The soil loses its rigidity and the ground cannot support, causing them to sink or collapse. From the first illustration, you can see the before and after a soil liquefaction happens due to an earthquake. And the second illustration shows a clear representation of how liquefaction occurs and how it affects the building above. Sa part A, yung first stage, ito yung bago pa mangyari ang liquefaction. Soil particles here are still in contact and are being held to each other. Then sa part B, dito na yung na-lose ang stiffness ng soil due to ground shaking. So dito na pinakita na naghihiwa-hiwalay na yung mga soil particles which causes the soil to liquefy. At this stage, this is where the soil turns into a sand-like pure grains and looks exactly like mud on the surface. Then, at the last stage, ito na yung aftermath of liquefaction. Happened after the earthquake. Loosen na yung soil matter and the building above it was already damaged. The water already increases above the groundwater level, which causes the soil underground, the surface, to turn into mud-like that leads the building to collapse. Here are some examples of the effects of liquefaction in a certain area. These images shows how soil liquefaction may greatly affect the structure. These events mostly happen in areas with saturated soil, areas with shallow water tables, and close to the sea or river that are susceptible to liquefaction. Effects of liquefaction on buildings. The first one is the buckling of piles. Pile foundations are embedded deep into the ground because of the soil support. But if the soil is not strong, the foundations buckle, which leads to collapsing of the structure. In the illustration shown, there are 4 stages of backing of piles after a liquefaction occurs in a certain area. The next one is spreading of ground. The soil starts to move in a downward direction due to the liquefaction. Slopes starting from an angle of 3 degrees are prone to lateral spreading. Due to earthquake-induced liquefaction, deformed section of the affected areas may happen after an earthquake. In conclusion, to reduce the damage of soil liquefaction, we must avoid construction on saturated soils. Soil study must be conducted before construction to check whether the soil is durable for construction. Soil mapping must be made mandatory.